Hello dear students. So this is our 12th lecture on these tensors. So if you remember that in our previous lecture we have discussed about those how to construct this Minkowski matrix and how you can distinguish, because you can have this Minkowski matrix for this Euclidean, or you can say that pseudo-Riemann geometry. So that will be different compared if you talk about the general geometry. And so there's only change of sign, so this is very clear. So I will not discuss that. So today's topic is, if you remember that in previous lecture we have talked about that how to construct, how you can write that Minkowski matrix in terms of those transformation elements, right? So I will write here. So we know that. So if you remember that, we can write that ds square, right? That means this is our that square of the length element. It should remain irrelevant, right? So or you can write this as, if you write that in terms of that Minkowski matrix, right? So because this will be equal to, okay. So this is very clear. So just check your previous, just check my previous video. So this is very clear. So you can write that ds square in this way, right? And similarly, ds prime you can write in terms of that some g of some prime. So these are basically again that. So this is how that this matrix, and it is in some new frame, in some primary frame of reference, right? And similarly, these are that length elements, or you can say the differentials in that primary system, right? So you can now transform, because we are basically talking about, we have two frames here. So this is one frame and this another frame, and this is some prime S prime frame and this is S prime. Right? So we have two frames. So how we can relate this S prime with this S, right? So let us write this. We can write this S prime in terms of that S, right? Multiplying by some that this transformation, that you can say that transformation matrix. So you can convert that this differential element which is lying in that S prime. So you can convert it in the unprimed frame of reference. That means an S prime frame of reference, right? So we can rewrite this term. So this will be equal to, and of this one. So if you remember that, so we can write this in terms of that chronicle delta. So I can write this as that's partial x prime alpha, partial x mu, because we need to, because so remember one thing, क्योंकि मुझे change करना है, I need to change this unprimed to some primed system while our indices are mu and nu. तो वहाँ पे जो हम indices use कर रहे हैं, so those are mu and nu, right? So I need to convert this from some alpha prime to some mu, right? And similarly, I can transform this from some minus beta prime to nu, right? Because I need to transform it into this frame of reference, right? Into this frame, right? So that I can convert by multiplying this matrix element, or this is purely a chronicle delta. And this will be, you need to write here, because there is mu, so you can write here mu, and then dx, right? Okay. And this is coming from here, because you know that if we have some vector a, if you write that a of alpha, so this you can write that partial x alpha by partial x beta. Yeah. We can write it this way, right? Or this is purely that delta of alpha beta. Yeah. Because in alpha equal to beta, so you are getting that a of alpha, right? So this is very clear. So I have repeated it many times, so I think it's clear. So we can, so this is our first term. So because this is our that delta alpha prime mu, and this is dx mu. So we can write that when mu equal to alpha prime, so you are getting that dx alpha prime here. Again, that's same, right? So this are the transformation matrices. So which basically helps us to move from some primer system to some unprimed system, right? And similarly, you can write for the second differential element, that dx prime beta, right? So this I can rewrite as, so this will be partial x prime. So you need to use a mu here. because so this is our we are using these indices that mu and mu. So this is very clear because mu and mu these takes values at 0, 1, 2, 3, and this is very clear to you, right? And okay, so that means okay, can rewrite. So let me rub this part because so I don't mess up these things with this thing with these equations. Okay, so all right. Okay, so this is our that right hand side, and similarly, so this can write our this our left hand side that is G mu. Okay. So now let us move it. So let's write it this right hand side. I will shift it to my left hand side, right? So this will be equal to that G mu. That's equal. Okay. So this will be. Or you can take this term out. So this will be equal to. What I wrote here. That's equal to 0. Okay. So we can write because this is our that length element cannot be equal to 0. So this is our that length element. Okay. And scalar because dx into dx new. So that means this term should be equal to 0, right? So I can rewrite this as so that means our g mu nu. So I'm using somewhere this partial somewhere this so that is to write a partial x squared. Okay. So just check if I'm right. So this one that g mu nu equal to this minus g alpha prime. Okay, so this is equal to so this should be equal to 0, right? Or you can write this as so g mu nu will be equal to write this first. So write first a transformation matrix, then we can write this as that partial x square alpha. Okay, right? This is equal to that. So g mu nu equal to that is alpha mu alpha prime delta sum delta prime mu. Okay, so you can, so this is very clear because if you put that alpha equal to that nu prime, so this should be equal to 1. So in that case, so this will be that mu nu, right? So this is how you can transform this how you can transform this Minkowski matrix from some this unprimed to primed frame, right? So with the help of these transformation matrix, right? So अगर मुझे you can take this inverse also by writing that g prime in terms of that g, right? So by multiplying the inverse of these transformation matrix or this the multiplication of these delta, right? So it depends upon so either you are going from some unprimed to the private system, right? Okay. So this is how we can write these Minkowski matrix in terms of that transformation matrix and how it helps us to go from one frame to another frame, right? So this was all about that what we have discussed in previous lecture, that Minkowski matrix, and so many things I don't remember this time. So now our next lecture is about that if you talk about these contravariant and covariant vectors, right? So so okay. So we need to discuss what is first, that's contravariant and covariant vector. Maybe you might have heard about these. What is that contravariant and covariant vector? By remembering that तो हम कह रहे हैं कि जो contravariant होता है तो it has that index in the upper superscript, and this covariant had that index in the subscript, right? So this is what we have learned. Maybe some of the students will be aware, but how we can define a contravariant and covariant, that's totally different. How we can define this? तो हम कैसे define कर सकते हैं contravariant और covariant, right? So first, if you talk about these tensors, so tensors are purely a mathematical object, right? So which basically transform in a different way. So if you remember that I have in one of my lecture I have discussed about the basis vectors, right? So not unit vectors, orthonormal unit. I am talking about these basis vectors. I can define a vector in terms of basis vectors also. Like if I have some vector, so vector A, so I can write this as some ax, ex. So this ex, ey, and ez, these are basically the basis vectors of, and ax, ay, and az are the different components of that vector A, right? So if you remember, with the help of that bracket notation, I already told you that how we can, if you know the component, so with the help of that completeness relation also, so we can calculate, if we know the one component, we can construct the whole vector, or you can take it as reverse also, right? So this is basically how we can define the basis vector. So these are not those orthogonal unit vectors. So these are simply those basis vectors, and which again represents represent the direction of these different components of that vector, right? So let's first discuss what's basically a contravariant vector and then a covariant vector, right? So as I already told you, if you talk about these tensors, so tensors, how you define tensors? So tensors are purely mathematical. So it is purely a mathematical object which transforms in a different way. Which transforms in a different way when the basis changes, when the basis of that vector changes, right? So it's a mathematical object which transforms in a different way. What I wrote here is basically purely a mathematical objective which transforms in a different way when the basis of that that quantity will change. So we can say that's purely a tensor, right? So if you talk about we have some vector in some three-dimensional space. So it has some basis along x, basis vectors along x, along y, and along z direction. So that means if we have this, so I cannot draw the three-dimensional this diagram here. So if we define here a vector, तो अगर हमारे पास ये vector A होगा, so it has these basis vectors will be along this one, along this, and along this direction, right? So suppose this will be some ex, and this is ez, and this one. So these are basically the different bases of this vector A, and uh, and you can say that if we understand this tensor, So as I already told you, it's purely a mathematical object. If you understand the tensors, so that means you are understanding the curvature of space-time. So understanding tensor basically helps us to understand the curvature of that space-time, right? So we can say that simply we are saying that a tensor of rank 1 is simply a vector. अगर हमारे पास एक टेंसर होगा which transform जैसे if you remember that like scalar we are saying that a scalar we are saying that how you can define a scalar, so we are saying that some quantity which remains invariant if you move from one frame to another frame. So that invariance of that quantity is called scalar because it remains same, its value remains same under the transformation from one frame to another frame. So that quantity is supposed to be scalar. And similarly, in the same way, tensors transform in that way, right? So we can say, that's why I wrote here that tensor basically transforms in a different way, right? So if you make transformation from one frame to another frame, right? And if you talk about that, if we have some tensor of rank 1, so that's purely vector. So that means vector is again a tensor. So if you remember if you have visited my the first or second lecture on tensor, so you might be you will be aware about this. So how we can define this scalar, that vector and tensor. So tensor vector lies somewhere in between the tensor and the scalar, right? So we are saying that if we have a tensor of rank 1, so that's purely vector. So that means if we suppose that tensor, so what about the scalar? So scalar is, so you can say that scalar is again a tensor of rank 0, right? So because, so that means we have then 3 raised for n components. So हमारे पास 3 raised for n component, n stands for, so what is the rank of that tensor? Suppose the rank is 1 here, so how many components it can have? So इसके पास 3 components. So 3 component means it can have that x, y and z component, right? And similarly, if you talk about a scalar, so scalar मैंने आपको already कहा कि we have this is again a tensor of rank 0. So that means, so this will be then 3 raised for 0. So for scalar, so that's equal to, so that means this scalar has only one component, right? And vector has 3 components. We can have tensors of different ranks like tensor of rank 2, tensor of rank 3. So that means tensor of rank 2 has 9 components, right? So we'll discuss maybe in coming lectures, right? So this is how you can define a tensor. And now our main topic is, let's go back to our main topic, that is basically how you can define a contravariate vector, right? So if we choose different bases, suppose I'm saying now, if we have this, so this is our this is the plane, and suppose this is our vector A, right? And these are our bases. So these are our basis vectors of that vector, right? Now if we change the basis, तो हमारे basis थे ये, suppose these were the bases, and ये हमारा vector था. Now I'm changing the basis. So if I change the basis, the so it so that means if you change the basis now, so if you write now, if we again plot that, this is our vector A, and our bases are now new one. So suppose this is our Ex, and this is our Ez, and this is our Eb. So if I change the basis now, right? So in that case, so you can say that the component of this vector will also change. So because the basis, if you change the basis, so the components will change. Because अगर हम यहाँ पे देखेंगे, I will give an example. Suppose if I have some vector, and the components of that vector are components of तो जो मेरा वेक्टर ए है, it has component that is 2, 4 and 6. So that means हमें we have to go to units of basis along this x, and 4 units along y and 6 units along z, right? So that means मुझे कैसे प्लॉट करना है? So that means this is our vector A, right? तो मुझे 2 यूनिट्स along x जाने हैं, 4 units along, so this will be 2 4 है. So this is not very clear because so that means हम क्या कर रहे हैं? We are basically going 2 units along this axis, 4 units along y and 6 units along z. So ये हमें component A देगा, vector A देगा, sorry, right? Now what I am saying now, अगर हम अब क्या करेंगे? If we double the length, so instead of that, I am saying that I am doubling the length. So in that case, our vector A will be equal to, तो इससे क्या होगा? So that means जो बेसिस यहाँ पे है, यहाँ पे बेसिस हमारे पास 2 थे, बेसिस वेक्टर्स 2, तो 2 बेसिस वेक्टर्स along x, 4 basis vectors along y and 6 basis vectors along z direction, right? तो अब मैंने क्या कहा? I am changing, I am doubling the length now. So doubling length means, so the component is, so instead of that, so I can show you, I am saying now, if I have now components of A are, that's 1, 2 and 3. Because if you remember that, यहाँ पे मैंने कहा कि so that means we are going 2 basis vectors along this x, then 4 basis vectors along y, and then 6 basis vectors along z direction, right? In order to achieve this vector, right? Now what I'm saying now, अगर हम length double करेंगे, तो instead of these 2 basis vectors, I'm only using 1 basis vector. Instead of these 4 basis vectors, I'm only using 2 basis vectors. And similarly for z direction, so I'm using only the 3 basis vectors, right? तो उसमें क्या होगा? So that means अगर हम, if you write now our vector, so that means this was our vector A, right? तो हमें एक basis vector along A जाना है, so this was ex. तो यहाँ पे 2 ही जाने हैं, यहाँ पे 3 जाने हैं. So this is our ey. Okay. So that means अगर हम, if we increase the length of the vector, basis vectors, अगर हम, if we increase the length of the basis vectors, number of components gets decreased. तो components decrease होते हैं, because this is very clear. तो पहले में हमने देखा था, अगर हम, if we use 2 basis vectors, right? तो instead of that अगर हम double length करेंगे, so that means by increasing the length, the basis vectors decrease. So that means the number of components of that vector decreases. So these are basically the components of that vector, right? So that means, hence here components are decreased by increasing the length. So that means अगर हम increase length करेंगे तो components decrease हो रहे हैं. और instead of that अगर हमारे पास 2 units, अगर हम 4 use करेंगे along x, so that means by increasing the number of components, that decreases the length of the basis vector. So that means how? So these are contrary to each other. That means number of components and the length of the vector. So that basically you are saying that this is how you can define the contravariant way of defining a vector. So this basically gives us the contravariant way of defining a vector. So how this, by changing the length, the corresponding the components of that vector will change. So that's basically called the contravariant, right? And similarly, if you talk about now the covariant, so covariant हम define करते हैं if you talk about the dot product between the vectors or between the basis vectors, right? So that means if you now, so instead of that, if you talk about now, because again, if you draw some we have some vector A, okay, and these are the basis vectors ex, and this is ey, and this is ez, right? तो हम कैसे डिफाइन करते हैं ये how we define this dot product? So that's simply that if you calculate that this, so that will be the simply the dot product between the vectors, right? So or you can write that this ax dot that unit this basis vector, right? So that means अगर हम यहाँ पे क्या करेंगे तो repeating the same procedure. Now instead of that, if we increase the length, the dot product will also increase, because dot product depends upon that If you talk about the dot product within the vector, so that is simply that A dot B is that mod B cos theta, right? तो अगर हम मैग्नीट्यूड इंक्रीज करेंगे, चेंज करेंगे, इफ वी चेंज द मैग्नीट्यूड हियर, तो उससे क्या होगा, तो जो हमारा डॉट प्रोडक्ट वो भी इंक्रीज होगा. Dot product will also increase by increasing the length, or by decreasing the length the dot product will also decrease. तो वहां पे डिफरेंट था, right? So there it basically says that by increasing the length number of basis vectors decreases, number of components decreases, or by decreasing the length number of that components will increase, right? So वहां पे that is basically how, that's the way how we can define the contravariant of a vector. And here I am saying now in terms of now the dot product. So dot product ये depend करता है, it depends upon the magnitude between the magnitude of the vectors, right? तो अगर हम यहाँ पे length increase या decrease करेंगे, instead of that 2 units अगर हम 4 units करेंगे, right? तो I am decreasing the length. तो decreasing length means that decreases the dot product. और instead of that 2 units, जैसे यहाँ पे वहाँ पे 2 units था, यहाँ पे 1 unit, यहाँ पे मैं basically क्या कर रहा हूँ, I am increasing the length. तो यहाँ पे जो dot product है वो increase हो जाएगा. So that is basically, that defines the covariant way of defining a vector, right? So this is how you can define covariant and contravariant. So in addition to that, so usually we are defining that the contravariant by putting some that index in the superscript, and similarly if you talk about this covariant, we are defining by putting some index in the subscript, right? So this is how we can define the contravariant and covariant. So in nutshell, I can say that contravariant is how this length changes, how length varies with the number of components of that vector. Here in covariance, you are saying that how the dot product changes by changing the length of that basis vectors, right? So this is the contravariant and the covariant way of defining a vector. Now, if you talk about now, so suppose because we have different coordinate systems, right? If you talk about now, if we use the in cylindrical coordinates, then, so let us define a vector A. So we can define it by arrow okay. So this is basically how you can define this ordinary vector. Ordinary vector, you can say that. So that is coefficient of that nth basis in some orthogonal system, right? And this is how you can define a vector. I'm putting some tilde in order to define it by some regular vector. So these are basically our ordinary vectors, right? So this is an ordinary vector, right? So we know that. So if you remember that, we know that our ds square, that's equal to okay. Now I'm putting here summation, so that means I'm adding these indices, right? Okay. So I'm putting here summation or mu, right? Now let us define now. We will define the g mu nu. So g mu nu I define as, so that is h mu square into, okay, because when mu equal to nu, so this is h mu square. So this is that square of the length, right? So this is simply that length square, which is some parameter. It is that the dimensions of that length. Okay. So we can rewrite this as, so ds square will be equal to, so that will be equal to, so this is purely an ordinary vector. So as I already told you, ordinary vector, you are defining that this is basically that if you write the coefficient of the nth unit basis in some orthogonal system, right? So that's basically and that is in an equivalence space. So that's basically how you can define an ordinary vector, right? And this is an ordinary vector, and this vector I am basically expressing in terms of these cylindrical coordinates, that's rho, phi, and z. And in addition to that, I added one more point that I'm basically putting here summation that indicates that we need to by Einstein's summation convention, you are basically adding them. Okay. And then what I did here, I basically put that this Minkowski matrix in terms of that square of the length multiplied by that. So that means this Minkowski matrix is simply that indicates our that square of the length, right? And that's h mu square. So now here, because this is our that conical delta, so if you put that mu equal to mu, so because if you put that delta mu equal to 1, mu equal to mu, and this is equal to 0. So we will use the first property here. That means if you put that mu equal to mu, so when you put mu equal to mu, so this summation goes like over mu, mu. So either of them. So either हम use कर सकते हैं mu or we can use mu. So I will put here summation of mu, and this is h mu, and this will be dx mu dx, right? So I can put here then. So if you just check it, because I'm putting here mu equal to mu, so this will be equal to 1, and this will be summation of mu h mu square dx mu dx mu, because mu equal to mu, right? So this will be equal to 1. So I can rewrite this term as, okay. So this one, this term, it corresponds to our length. Why? So what I am saying now, this term, or you can say that this term or this term, this corresponds to our length, right? Or you can put it this way. Okay. So that means h mu dx mu, h mu dx mu. Huh? So this again, this one also corresponds to our length. Why? Because what is ds square? That is square of the length element. So that means you are basically multiplying, because this is this is total indicates our length, and this length. So the length square, because this is our ds square, right? So that means you are saying that this g mu nu. So if you check that, so this g mu nu. So what I wrote here, the g mu nu. So that is equal to this one, right? So this g mu nu converts that differentials. So it basically converts this. It converts this differential. So these are differential elements, some dx, dy, or dz, right? So this g mu nu, this matrix or Minkowski matrix converts our that differentials into lengths, right? So that means this g mu nu. So the significance of g mu nu, it basically converts that differentials into or dx mu into the length. तो ये कन्वर्ट करता है डिफरेंशियल्स को इन टर्म्स ऑफ लेंथ. सो दैट मींस लैंग्वेज इज आवर, सो लैंग्वेज इज आवर दैट h mu dx. Okay. So this was how you can define an ordinary vector. Let us define now. So let us define contravariant. So that means, as I already told you, so contravariant हम usually define करते हैं by putting, हम index को superscript में लिखते हैं, that's contravariant vector, and similarly by putting that index in the subscript, so that indicates our covariant vector. So let us define first that contravariant vector. So let us define now. Let us define that. Sorry. Okay, great. Right. this is how you can define a contravariant vector, and this is simply you are representing in terms of that ordinary vector, right? Okay, divided by the length, because that ordinary vector will be h mu into a mu. So that's again that corresponds to that, right? So this, or you can write that. So this is equal to, you can write that a mu will be. Okay. So that means this is an ordinary vector, and this is our that contravariant vector. So that means I'm basically converting this are contravariant vector and this ordinary vector. So that means I can represent that contravariant vector, because what we have, so we have these ordinary vectors. So we have some vector in some rectangular coordinates, cylindrical or spherical coordinates, right? So that's that ordinary vector, right? So I'm basically converting my ordinary vector, or you can write it in terms of that contravariant vector, right? So this is what I wrote here, that AB will be equal to this one, right? And this is our ordinary vector, and this is our that contravariant vector. So let's write now what's our ds square. So our ds square will be, that's equal to, okay. So I'm putting now. So यहाँ पे, if you remember that, so this is how we can define that, because this is again that a mu. So these are basically the two contravariant vectors, right? So I can write that contravariant vector in terms of that ordinary vector and divided by the length. So this is very clear, right? So I can write it in this way also, because if you so in our first or second slide we have written that in terms of the dx mu or dx mu, right? So again I can write it in this way also in terms of those vectors, right? So this will be equal to, or you can write that. Okay, so you can write this as, so this will be equal to. So this you can write in terms of that h mu square. Okay. So this is very clear, right? Or you can write this as, because this is the one that how you can define a contravariant vector. So using this definition, you can write this a mu in terms of this one and that b mu in terms of this one, right? So you can write that. Or ds square will be equal to. Okay. Now because using the property of that delta, you can then mu equal to mu. So that's equal to 1, right? So this will be equal to. Okay. Because mu equal to mu, so ये यहाँ पे बन जाएगा b mu and this h mu. So because this will cancel, right? So we can write this as. So this you can write as ds square will be equal to additional mu. That's our a mu. Okay. So this is that how you are writing that ds square in terms of those uh, ordinary vectors, right? So these are ordinary vectors because I'm transforming, I'm changing that contravariant in terms of that. I'm writing that contravariant vector in terms of these ordinary vectors divided by the lengths, right? And this is basically that. Or you can rewrite this as, so this will be equal to, if you expand this, because this shows summation over that mu, so this will be that. Okay. Now we can define now. Also, we can write now. We can write that a mu as. So this you can write in terms of that. Right? So that means, so if you remember that, so this is how you can write that this is our regular vector and this is our dual vector. So how you can, okay.